the second part of today's class, we're going to look at thermodynamic processes. Thermodynamic processes are certain simple processes that you can do using heat, using work, using internal energy that creates some useful work. So this is used a lot in heat engines, any machine or engine that works based on heat, like maybe refrigerators, heaters, locomotive trains, and many examples that we're going to look at next class. But before getting there, we have to learn about the basic thermodynamic processes that happen inside of these machines. So we're going to look at 4 examples of thermodynamic processes, and for that we're going to need a way to visualize it. So the way in which thermodynamic processes are visualized is that you can imagine a container that is filled with gas. So inside it's going to have molecules of gas. I'll draw them as blue molecules. And they have some internal energy, right? And the gas is closed up so it can't leave because it has a piston on top, which is this little like bar on top of it that can go up or down. So it's held from a motor or something, this little piston, and it can go up and down. So the gas inside has something called state variables that measure how it is in that moment. And these state variables are the pressure of the gas, pressure P, the volume of the gas inside of the container, volume V, and the temperature of the gas, temperature T. So as long as everything is kept constant and nothing moves, pressure, volume, and temperature will stay the same. But if you start doing things like putting in some heat or putting in some work, doing some work on the gas, the pressure, volume, and temperature will start changing. But you can keep one or more of these things the same in order to get some useful energy out of it. So an example of this would be if you wanted to keep the pressure of the gas the same. So that is a process called isobaric. Isobaric process. So I'm going to write here the processes. So isobaric process is when you keep the pressure the same, because baric is about pressure. A barometer is something that measures pressure, as we saw at the end of last year. So what happens in this process? Isobaric, pressure is constant. So in order to see what's going on, we might want to graph this in a type of graph called PV, because it's pressure and volume. So let's see, right here I'm going to draw a P, so this is volume, a PV graph, pressure and volume. We don't care about the numbers yet, we just want to see how the pressure and the volume change. So what we're going to do is we're going to either put in some heat, so that means heating up from below here with some fire or something, or we're going to do some work, yeah, which is trying to push the gas. But if the pressure is going to stay constant, when you heat it up, it wants to expand, right? So it would gain a lot of pressure. But if you let it expand freely, if you let it move the piston at will upwards, then the pressure will stay the same. It will expand, so volume will increase, but the pressure will stay the same. So basically, an isobaric process in a PV graph would mean that the pressure stays the same, but as time passes, the volume increases because the gas wants to release some pressure by getting bigger. So the graph would look something like this. Yeah, so it would go in this direction. At the same pressure, an initial pressure, it would increase in volume. Yeah, so the gas would be doing some work on the piston because it's moving it up. And work is when a force moves something. So the gas is doing work on the piston. And it's being heated up. So if we wanted to see what happens with this equation, we would get both heat and work. Both of them would be there. So this is let's see. So the defining property, let me write it here. Defining property of an isobaric process is that the P is constant, right? Constant pressure. So the first law of thermodynamics would look just like normal. The change in internal energy of the gas would be given by the heat added to it plus the work done on it. Notice that in this case, work is not done on it, but the gas does work itself. So that W will be negative. We'll look at that better in a second. So that's one type of process. I'm going to draw a blue dot here so that you guys know that isobaric is this blue one. But there is another one called isovolumetric. Isovolumetric. Right? So in isovolumetric, as the name might suggest, the volume is constant. So now V is constant. So you might start noticing that iso means the same, doesn't move. So isobaric, pressure stays constant. Isovolumetric, volume stays constant. So what's going on here now? We want the volume to stay constant, so we fix the piston where it is, and we leave this volume to not change. The gas can't push up, and the piston can't push down. It's fixed in its location. So as you heat it up, the pressure of the gas is going to increase, right? So the pressure is going to increase while the volume stays the same. So as time passes, the volume will always be the initial volume, but the pressure will increase. So isovolumetric looks something like this. Sorry if that's crooked, but it's supposed to be straight up. So isovolumetric is straight up in the PV graph. So in this case, because I just told you that work is when a force moves something. But if the gas isn't allowed to move the piston, or the piston doesn't move the gas, there's no work. Yeah? So this also means that work is zero. There's no work. So in this equation, we can ignore the work, and the first law applied to an isovolumetric process would just be these two. So that is delta U equals Q without the W. So that's that second process. Now, what about third process? There's four. So the third process is called isothermal. Isothermal. So again, by knowing that iso means same or not changing, and thermal comes from temperature, we can tell that the defining property of this process is that the temperature is constant. Temperature is constant. So remember, I had told you before that the internal energy was proportional to the temperature. So if we don't change the temperature, we're not going to have any change in internal energy. So this also means that the change in internal energy is zero, because it's going to stay the same. So we can ignore this side of the equation, pass one of the two to the other side, so get a negative. So we're going to have, in this case, only Q and W with a negative. So Q will equal negative W. That's how an isothermal process is applied to the first law. So how would this look? In this case, both pressure and volume would change. The heat comes in, but the gas can't increase in temperature. So it wants to change phase, it wants to move up, it has more pressure. So it's going to have less pressure as it moves the piston up, more volume as it expands, but the temperature is going to stay the same. So in a pressure-volume graph, both things are going to change, pressure and volume, right? So the gas is going to expand, pressure is going to decrease while volume increases. And it looks like a curve. So it actually looks something like this. So it's a curve going down because pressure decreases as volume increases. That is the isothermal process. And the fourth and last process is not called iso anything, it's actually called adiabatic. Adiabatic process. And what adiabatic means is that no heat is allowed to come in or come out. So no heat, so Q will equal to zero. So that means that now we turn off this fire and there's no heat anymore. So things are going to change because the piston is doing work on the gas, or the gas is doing work on the piston, but not because of heat. So in this case, Q equals 0, the Q disappears from the equation, and we only have delta U and W. So the change in internal energy will be equal to W because Q is now 0. And how will that look? Well, there's still changes in pressure and volume because the gas will still expand and contract as work is done on it by the piston, or as the gas does work on the piston. So that can still change, but there won't be any heat. But that still means that the pressure and the volume will be changing at the same time. As pressure decreases, volume increases, just like in isothermal. So it also looks like a curve. It's usually a curve that goes below the other one, so it's steeper than in isothermal, but it still looks like a curve. So again, we don't care about the numbers, we only care about how these processes look. So an isobaric looks like a straight horizontal line because volume changes while pressure stays the same. Isovolumetric looks like a vertical line because pressure increases as the volume stays the same. An isotherm and an adiabatic look like curves, but an adiabatic is steeper than an isothermal because in both cases, pressure and volume are constantly changing as something else stays the same. In an isothermal, it's the temperature and the internal energy, and in an adiabatic, it's the heat. There's no heat input or heat output. So those are the 4 possible processes. Now the last thing I wanted to mention is how to calculate this work. So heat, we know how to calculate it. We figured it out the previous classes. And the change in internal energy is heat plus work. But how do we calculate work when we're talking about a volume of gas and a pressure of gas? So the equation is actually like this. Work equals negative pressure times the change in volume. This is the equation for work. Negative pressure times the change in volume. That means that when the gas expands, it's going to do work. So this is the delta V is going to be positive, so the work is negative. So basically, work is negative. Work is negative when the gas does work. When gas does work. And instead, if work is done on the gas, or the piston does work on the gas, it's going to contract the gas. So the volume is going to decrease, and this delta will be negative. So work is positive because negative times negative gives a positive. So work in total is positive when work is done on the gas by the piston. On the gas. Right? So this is going to help you with the worksheet later, these 2 cases. Work can be positive or work can be negative, depending on if the gas does work on the piston or the piston does work on the gas. And one last way that we're going to measure this work, but not specifically with numbers, maybe a couple of times, is using the graph. So one thing that people discovered and was very useful is that because work depends on pressure and changes in volume, it can be determined from the graph alone. What they discovered is that the work is equal to the area under the curve. Under the curve. So for example, if you wanted to find the work done during the isobaric process, the one that's a horizontal line, you just see from where to where it goes, and this whole area you calculated by multiplying and getting the area of this rectangle, and that will be the work done by the isobaric process. If you had a way to calculate the area under curves, you could get the work done by this pink isothermal process. The area underneath this whole curve would be for the isothermal process. So it's just these 2 ways. You can either calculate work with the equation, negative P times change in volume, or with the area under the curve. And that's it for thermodynamic processes.